I think we're missing, what, Troy and, yeah, Erica. Anybody else? Ah. Hmm. Okay. Wait, Walter, do something?
I just get to stretch.
Ah, I see. All right, well, I'll get started. Any questions about anything before I dive in? Excuse me. Well, that'll be loud. Um, so, if you're a big picture kind of person, I think you'll like today because what we're going to look at, it encompasses much of what we've done this semester already. And there are actually some proofs in Chapter 10 which, recover some of the things we found before in specific cases as part of a more general trend. And so it's very very satisfying from that aspect. But let me just begin with a definition of what a ring is. So here it is. Definition. And here are the axioms. For a ring, for a set R to be a ring, we have for all A, B, C in the ring, the following. So you have A plus B plus C is equal to A plus B plus C in the sense that it's associative, okay? So you also have, let me call this number 1. Number 2, we have that A plus B is equal to B plus A. Number 3, we have that A plus minus A is equal to 0. Number 4, we have that A plus 0 is equal to A. All right. And in addition to that, well, actually in addition, I'm talking about multiplication. I should say in multiplication. Sorry. Oh, I'm sorry. That's pretty horrible. Okay, so A times B times C is equal to A times B times C. In any other class, I would not write this multiplies. I really hate that notation. This multiplies. So, I mean, almost in any other class, I would either use juxtaposition or dots here to denote the multiplication. Or if you're in abstract algebra, you might put like a little star or something. But anyway, I'm sticking with Stillwell. The multiplication's also commutative. So A times B is equal to B times A. And A times 1 is equal to A. And A times 0 is equal to 0. So this is how addition works. This is how multiplication works. And there's also a distributive law. Okay. There's a distributive law which connects these two things. We have distribution following distributive property. Okay, so the distributive property is that A times B plus C is equal to A times B plus A times C. All right. A little bit more fine print. What should I really say? I mean, to be more axiomatic, to be more careful, what should I say about the quote-unquote plus thing and the quote-unquote times thing, to be a little bit more abstract here for a second? We have addition, which is actually a mapping from the Cartesian product of R in itself back to the R. So addition takes in pairs of things in the ring. and it gives you back another ring element, right? And uniquely so, it's a function, all right? It's a single valued assignment. And likewise, the multiplication, same thing. It's also a function from the Cartesian product of R with itself back to R. Now, a little bit more fine print. This actually, what I've actually defined, let's talk about some words here. The first four things, all right, actually, if you take what I wrote in red for the plus, all right, paired with 1, 3, and 4, so here's a comment. The fact that plus from R cross R to R is a function paired with axioms, again, 1, 3, and 4, makes R a group with respect to addition. All right? A group is something where we have an identity, in this case an additive identity 0. The operation's associative, and everything has an inverse, right? And also the operation is a function from the Cartesian product back. In other words, the operation is binary, it's closed, okay? Excuse me. If we throw in 2 to the mix, then we can say a little bit more. We can say it's an abelian group. With 2 as well, we get a abelian group. Okay? So a ring is really a group, an abelian group under addition, paired with an extra structure called multiplication that interfaces with the addition in a very specific way. Now, some people would actually say a little bit more. They would say that this is a ring with identity because this 1 is the multiplicative identity. And even for you guys who are going to be teachers, it's important to know this language, right? We need to know the difference between a multiplicative identity and an additive identity, right? It's one of the fundamental confusions of students when they're younger, is confusing these two concepts in places, right? Anyway, so 1 is a multiplicative inverse, identity. And you could talk about a ring without a multiplicative identity. Some people use the horrible fun that a ring without identity is an RNG. That's not just a joke. You'll find that in lots of books, okay? But anyway, for us, let us agree that a ring has identity, and it's a commutative ring. So this right here makes R a commutative ring. Almost without exception, when people talk about rings, in usual contexts in mathematics, they're talking about commutative rings, right? Probably if you find yourself needing to assume commutativity in the ring, it's probably okay, all right? Non-commutative ring theory is really different. The rules of the game are much more complicated, and it's not as well known. We have worked with a non-commutative ring. The quaternions are a non-commutative ring. You saw how much subtle things were there. In contrast, everything else we worked with has really been commutative ring for the most part. All right, so this is a ring. Any questions? What does this look like? What's the quintessential ring? Yeah, the integers. So examples. So of course, the integers, the Gaussian integers. Let's see here. How about the these guys, right? What else do we work with? How about the Eisenstein integers, right? So one of the goals in this chapter, and of course the Hurwitz integers would not fit. I mean, the Hurwitz integers we'd have to drop the commutative, right? But otherwise, they're also satisfying these properties, right? Um, so one of the goals in this chapter here is to try to understand what this word integer, try to understand how to properly abstract the notion of integers to other contexts, right? So our starting point is to define a ring, because a ring really captures the essence of what it means to have integers. Yeah.
What would there be an example of where like a times 0 would not equal 0? There wouldn't be a 0 in that field anymore.
Well, why would a times 0 not be 0? There might just not be such an element.
So you're saying like the empty set would not satisfy all the types?
You can find examples where there's an additive identity, but not where that additive identity doesn't multiply to 0.
Like natural numbers have its own?
Just take your favorite, I'm not disputing, maybe natural number, but I'm saying, what I'm trying to say is you could take your favorite additive, your favorite abelian group under addition, right? And then just define some stupid multiplication on it, which doesn't respect these rules. You could define some multiplication which doesn't multiply 0 to 0. Maybe your multiplication is something stupid where everything multiplies to the same element or something. I don't know.
Oh, okay.
You could define multiplications which aren't what we think of in ordinary speech as multiplication. But yes, the familiar examples of multiplication. That's the point. Is this is something that is common to all familiar examples of multiplication, right? And the point of this abstraction is once I prove something about a ring, right? I've proved it not just for one example, but for all of those examples. And that's the efficiency of our method, of our abstraction, right? That's why we use abstraction. Well, it's part of it. Okay, so divisibility we've talked about before. What does it mean? Really? Hopefully this wasn't a Ming text. Ming texts come in like half dozens. He doesn't believe in email. He believes in like, oh, exciting. Anyway, I can't sit here. So divisibility, right? We defined divisibility. I talked about divisibility like 3 or 4 different times in this class, right? But we can define it in general for an arbitrary ring. The definition, A divides B for A comma B in the ring, if and only if there exists, let's say, M in R such that what? B is equal to what? AM or MA, right? I mean, it's commutative, so thankfully we're not we're not trying to flesh out non-commutative ring theory. I would need more lectures for that. I'd have to say left, I'd have to say right. There'd be much quibbling. There it is, though. That holds just as well for the integers as it does for the Gaussian integers, as it does for the Eisenstein integers. I'm trying to keep myself from saying Hurwitz. There we got to talk about left and right. But anyway, that's it, right? And now that's not just it, right? So we can also talk about units. Definition, what's a unit? U, an element of R, is a unit if and only if what? Units are divisors of 1. So U divides 1. So that's the definition of a unit in an arbitrary ring. That will pick up the units we found in the Gaussian integers. That picks up plus or minus 1 in the integers, right? That picks up the, well, I would tell you they're the 6th roots of unity that are the units in the Eisenstein integers. We wrote them in terms of the 3rd root of unity, but if you look at this guy, right? I would point out to you that the units, they're actually 60 degrees apart, right? There's like, excuse me. Maybe this is the wrong day to start using a mic. Oh well. Haha, take that, Troy. So, this, basically this one right here, if you know complex, if you don't, it's okay. But this is really e to the 2 pi I over 6, right? Which is cosine pi over 3 plus I sine pi over 3. And, that for what it's worth is 1 plus I root 3 over 2, Now this one over here was what we called the third root of unity, right? Or zeta 3. But this is also equal to, if I call this thing, let's say omega sub 6, this is equal to omega sub 6 squared. By the way, this one down here is omega sub 6 cubed. This one is omega sub 6. Oh, wait a minute. I lost one, didn't I? I've only got 5/6 roots of unity. Something is missing. Yeah, minus 1 probably should be there. Sorry. Yeah, and that should be a 5 then, and because minus 1 is omega. It's the 6th root of unity. Yeah. Cubed. Yeah. I can't do math. All right. Somebody take away my license. Let's see here. 5th, and then of course 1 is equal to omega, the 6th root of unity to the 6th power. Because if you take this and you raise it to the 6th power, you get back e to the 2 pi I, right, which is equal to 1. So that's a unit, but a unit is just a divisor of 1, right? Now, for the ones I have listed up here, the number of units is finite, right? But if we look at integers over other things, there could be infinitely many units. Yeah. Z adjoin the square root of n? Yes. We usually insist on n being square free because otherwise it wasn't that interesting. But yes, if we have z adjoin square root of n, that would be, if n is positive, then the units, exactly, so let me stop talking, start writing. So another example would be something like you just said, z adjoin, square root of n, where n is square free, which is just a fancy way of saying n is not equal to like a squared for some a, right? And in this one, if we're still using the norm as we have been, right? If you look at something like a plus b root n, well, and now I've jumped the gun. There was something else I was going to say before I got to this point. Curses. If we have a norm, then it also follows that the now I'm all out of order. Sorry, but you remember things I haven't said yet, but I will soon say. The norm must also be 1, right? And if the norm of this is 1, so we did it before, but I was going to do it again. So the norm of this being 1 is that's 1 is equal to a squared minus nb squared, right? And if n is a positive integer, well, this is nothing more than, what is this? This was something we studied a while ago, but this is Pell's equation, right? Pell's equation actually is what this is, and there are infinitely many solutions. Implies infinitely many units in this thing. All right. Let me just tell you some things he tells you in the chapter at this point, and it's maybe slightly out of order, but it seems like the right time to say it. It turns out that if you look at these sorts of rings that are built from basically the adjoining the square root of a negative integer, all right? These are the so-called imaginary, these are integers of imaginary quadratic fields, as I will define carefully shortly. It turns out that that's as many units as you can get. There's like no other example out there with more than 6 units. Because for the imaginary, for the imaginary quadratic fields, it turns out we're able to argue that that's as many units as you can possibly get. That's something that's proved in this chapter. On the other hand, for adjoining, the square root of not a negative integer but a positive integer, the units are just solutions to Pell's equations. So that's that. Another fun fact, unique factorization, right? We've seen unique factorization works in the Gaussian integers, in z adjoin square root of minus 2. We had to add those extra half integer points, right, to get the Eisenstein integers. Also, we have unique factorization there. But we don't have unique factorization, for example, directly in the square root of minus 3 because we had to pair it with Eisenstein integers. And we also don't have unique factorization if we look at z adjoin the square root of minus 5. Yeah, Jess? I think there are infinitely many. I think there are infinitely many. Well, what kind of... Are we talking about the Hurwitz integers? In the Hurwitz integers, there were 24 units, as you will become painfully familiar with in one of your homework problems. They form a group. The units form a group. Like, for example, in the integers, there's a multiplicative group, plus and minus 1. 1 times 1 is 1, minus 1 times 1 is 1. So, like, minus 1 is its own inverse, 1 is the identity. It's a stupid group. It's got 2 elements, but 1 and minus 1 form a group, the group of units in the integers. If you look at plus or minus 1 and plus or minus I, you have 4 things. Multiply any of those things, you get back to where you started, right? So the group of units in the Gaussian integers also, is a group in the technical sense of group multiplicatively. I guess the group of units in my last thing I wrote over there, maybe it's also a group, but it's an infinite group. But we found its structure too. We found how to multiply it. In fact, that's how we built part of how we built solutions. So, to Pell's equation.
So even though like J and K strings like even though they're represented as a matrix, would they still be the same units? Do they divide them?
Yeah, I think the versors, the I, J, K, and related things are units. But there's also the like omega, the 1 plus I plus J plus K over 2 is also a unit in the Hurwitz integers. If you talk about the quaternions alone, I'm getting off track here. I must cease my comment. There's more to say. What I wanted to say, though, before I went on here, he spills the beans a little bit later in here. I was starting to say something. When is there unique factorization? It turns out. So first of all, one of the things proved in this chapter is that there's just as much as only up to 6 units. This is it. This is as much as you can get for like an imaginary quadratic field. But more than that, Gauss in 1801 proved that the only imaginary quadratic fields which, the integers over them allow unique factorization are d equals minus 1, minus 2, minus 3, minus 7, minus 11, minus 9, minus 43, minus 67, minus 163, and that's it. Everywhere else, unique factorization fails for the things like either z adjoint square root of minus 2 or the Eisenstein integers analog for those other numbers. Now Gauss found that in 1801. It was proved in 1967 by Baker and Stark. But get this, the real quadratic fields with unique prime factorization are still not known, nor is it known whether there are infinitely many of them. The real ones, he's talking about this. These are the integers for a real quadratic field. Okay. I'm even using this word, quadratic field. I need to explain what I'm talking about, okay? So it turns out that the question of unique factorization is actually not even known over here to this day. When it's possible, when it's not. That's kind of exciting. I think that's something that you can understand where you are, even if you can't solve it. I mean, I guess if you could solve it, you probably could like stop working on math here and go work somewhere else. Just guessing. Anything that's that obvious a question that has been sitting there unsolved for this long? I don't know. Maybe it's just hopelessly technical. All right, let me get back to work here. I digressed. So sorry. So, so that's a ring. What's a field? What's the difference between a ring and a field? So a field is a ring such that every non-zero element x, and you usually use F for field, has x inverse also in the field, such that x times x inverse is equal to the multiplicative identity. Can you put this into words in terms of units? What does this equation say about x? What does that say about x? Yes. But in terms of divisibility, what does it say about x? X is a divisor of what? 1, right? This says that x divides 1. Therefore, x is a unit. That's right. In other words, a way you could define a field is the following. You could say a field is a ring where every non-zero element is a unit. That's just a fancy way of saying everything that's non-zero has a multiplicative identity. So a ring is closed under addition, multiplication, and subtraction, by definition. A field is also closed under division. That's the new thing, is we also have closure under division. You can always define A over B. So what are examples of fields? Real numbers, right? Let me put it up here. The one thing that I probably left out of this discussion here, because I chased a rabbit or two, I was probably supposed to tell you what a prime was there, but we'll get back to it. And so this was examples of rings. All right, Aaron. And to be more specific, excuse me, these are rings which are not fields. In the standard sense, at least. And my other set of examples, here's our fields, all right? So, for example, f equal to, so I'm going to say this, you could talk about the rational numbers as an example of a field. You could talk about the field which is formed from taking the rational numbers, right? And then adding a new element, adjoining the element I to it, all right? So Q adjoin I is what's called, I'll use this notation. We used square brackets before. When you use the parentheses, what that means is you're adding something new to the set in such a way that addition, multiplication, subtraction, and division are closed back on it. So you add enough things that if I add I to it, I can still get back to whatever was there under division as well. If I just use the square brackets, that means that you're closing the set under addition, multiplication, and subtraction, but not division. And it turns out one of the theorems that he has in this chapter is that this is equal to this. So if you're like, I can't tell the difference, that's good because there's no difference. But I will make good on proving that here shortly. This one, Q adjoin, well, the field So this is the so-called quadratic, the imaginary quadratic field built from taking the rational numbers and adjoining the square root of -2, and so forth. Now, you guys told me something else. You told me, well, you could also look at the real numbers. That's true. That's a field. The complex numbers, also a field. While we're at it, z mod pz is a field if p is prime. Because if p is prime, everything has a multiplicative inverse, right? Because the GCD of p in any number is 1, which means that you can look at Bazau's identity and find the multiplicative inverse. We did that earlier. So finite, that's a finite field, right? And there are more things. In 422, you'll look at this concept called field extension, and you'll systematically show how to do these sorts of things in terms of other constructions. That's not what I'm going to do in here. So we're just going to take a slightly less constructive excuse me, approach. Although I might construct them. I'll shut up. So these are the integers over this field. These are the integers over the field, the extension of q by I. These are the integers over that. Over that. These are the integers over q. I think just q adjoin square root of -3. I goodness gracious, I'm not absolutely sure about that, but all right. So that's the difference between a field and a ring, and we work with both, right? So it turns out that looking at things in rings has been productive for solving specific Diophantine equations this semester, right? But often, if we put that in a slightly larger context of like the underlying field, we've been able to do calculations with fractions, which have helped us to see past certain issues. So it's usually the case that it's nice to be able to kind of stick what you're working in a slightly larger context, because you can, well, it's like solving a quadratic equation in light of the complex numbers versus without it. If you don't have complex numbers, then it's just like every so often you can't solve it and you don't really understand why. If you have complex numbers, you understand exactly why you can't solve it. It's because the solution is somewhere else, right? It's just that. So so here's yet another definition. This is due to Dedekind, who I think we owe much of what we're doing to him. And so this brings us to I have to define, I've been throwing this word around like, those are the integers over this, those are the integers over this. Now I want to make good on defining that carefully, all right? So that's section 10.3. And it begins, excuse me, with this definition. A number C rather a number alpha in the complex numbers, okay? So, as abstract as this is, what we're talking about right now, it's not that abstract. Everything here is happening inside the complex numbers, okay? At this point, earlier, a ring was abstract, okay? I mean, it could be matrices. Well, that wouldn't be commutative, usually. Anyway, a number alpha in the complex numbers is algebraic. Okay. If basically there's a polynomial which annihilates it. So am alpha to the m plus am minus 1 alpha to the m minus 1 plus dot 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 plus a1 alpha plus a naught equals to 0, where what? am minus 1, and so forth and so on, all the way down to a1 to a naught. These are all what? You might think rational numbers, right? But no, these are integers. So that's the definition of algebraic. And so the degree of alpha is defined to be m if no, lower degree polynomial also evaluates to 0 for alpha, all right? Okay, so what are algebraic integers? It's a subset of complex numbers, all right? What's the structure of these algebraic integers? What can we say? Can you guys think of any examples? Let's see here. How about this? Think about a rational number. Think about z is equal to p over q for some p and q in the integers, right? Is this an algebraic integer? If so, why? I should say alpha. Sorry. I'd really like to say that this thing is equal to, for the sake of language, that this is equal to, let me say f of alpha. So like, in that language, I could also talk about f of x equal to what? am x to the m, a1x plus a0. That way I can distinguish between the solution and the polynomial. They're kind of blended together in Stillwell's definition, which is fine. Yeah? So f of x equals what? Is what I'm trying to get you to say. So you say q times x minus p. All right. Let's see here. Let's try it out. Take it for a spin. F of alpha is what? Q times p over q minus p. Hey, the q's cancel. So we get p minus p, otherwise known as 0. Right, so rational numbers are algebraic integers. Oh, did I say algebraic integers? Because I shouldn't. Rational numbers are algebraic. Stop. Over C. I mean, they're an example of an algebraic number. Okay. I did not say that they were algebraic integers. I should not say that. I have not defined that yet. In general. What's their degree? It's just 1, right? Yeah. Square root of 2. How about square root of 2? Is that an algebraic number? Can we define it by the vanishing of some polynomial? What is the f of x in this case? Yeah. So as you can see, f of alpha is equal to, oh, wait a minute. Yeah, sorry. Okay, I'm sorry. Okay. What's the degree of alpha in this case? 2, right? Right. Actually, Stillwell claims a little bit more here. He says rational numbers are the algebraic numbers of degree 1. I assumed that alpha was, right? Here I've done one direction of that. I haven't done the other direction. He's saying that the only algebraic numbers of degree 1 are irrational numbers. How would we kind of go the other way? Suppose you have an algebraic number of degree 1. How can you prove it's rational? Put that right here. So suppose alpha is degree 1. So that means that there is some g of x with like some numbers, right? a1 times x plus a0 such that what? G of alpha is equal to 0. That's to say that alpha is degree 1. But what does this give you? This gives you that a1 times alpha plus a naught is equal to 0. Therefore, alpha is equal to minus a naught over a1. But hey, that is a rational number because we know that the coefficients are integers. So it's not just that integers are degree 1 algebraic numbers. Excuse me, words. It's not just that rational numbers are degree 1 algebraic numbers. They're the only ones. Okay, that's it. Now, it gets more complicated. For example, you could look at, say, alpha equals to the cube root of 2, and you could look at beta equals to the 5th root of 3, right? And it's fairly obvious that you have alpha cubed minus 2 equals to 0, right? And you have beta to the 5th minus 3 equals to 0, right? Fine. I mean, you could do that. I'm pretty sure, I mean, I'd like to tell you that the degree of alpha is 3 and the degree of beta is 5. I'm not entirely sure about that. It might or may not be true. I'd have to do some thinking about that, whether or not I can find those numbers as solutions to lower order polynomials. Maybe I can. But here's a fun fact for you. Alpha plus beta is also algebraic number. So what's a polynomial with integer coefficients which that number appears as a solution for? I personally can't tell you. But we will soon give a proof that shows that it isn't necessarily the case that there is such a polynomial. The proof is based on the determinant. So, in fact, and this is not even proved in this book, but it can be shown. So here's just a fun fact for you. Fun facts are those ones which we don't prove. Fun fact, the algebraic numbers over C form a field. So that means that, I mean, for example, there's got to be, if you've got square root of 2, like somehow you can get 1 over the square root of 2. How would you do that? Yeah, exactly. But that's not allowed. It is forbidden. Ah, yes. But you can fix it, right? F of x, 2x squared minus 1. Now we are in the world of integer coefficiented polynomials, which means it is allowed, right? But you see that the coefficient, the leading coefficient, it's not going to be 1, right? I mean, being able to make the leading coefficient not be 1 is important to be able to find the multiplicative inverse elements in these algebraic numbers, right? So if I was to, for example, if I was to forbid this being 2, if I was to insist that the leading coefficient of the polynomials which define the number is 1, then I wouldn't have 1 over root 2 in the set anymore, would I? And that leads us to the definition of algebraic integer. An algebraic integer is an algebraic number whose defining polynomial is monic. So if you want to add integer here, if it's a number and all of a sudden I've got to say, maybe I needed it before, I don't know, but I need it now, is an algebraic integer if f of alpha blah 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 with a sub m equal to 1. So you have to have a monic polynomial, leading coefficient being 1. So, for example, the square root of 2 is an algebraic integer. Excuse me. Because what? because we had a monic polynomial which defined it, right? Whereas, well, I think this is also an algebraic integer. This is also an algebraic integer. Okay. If I can just keep from coughing here, I'll be good to go. Now, but, algebraic integers, they're not just integer linear combinations of the objects which are defining the set. Like this one, remember what this was? This was, what was it, -1 plus I times the square root of 3 all over 2. So we ended up needing actually half integer combinations to form the quote-unquote integers over the in the Eisenstein case, right? And we said, well, they really are integers because they have unique factorization. They behave like integers, right? In fact, they have a ring. They have a ring structure with the unique factorization property. Okay, so I'm just saying, to say algebraic integer does not just mean that, well, I mean, this is, look at this. I mean, I'm saying that square root of 2 is an algebraic integer. So that's kind of out there, right? So algebraic integers include lots of things like irrational numbers and all sorts of things. It's a rather general concept. There's lots and lots of algebraic integers. It's kind of huge. Yes?
I was just only asking because I didn't know if it was...
Go for it.
Defining the definition. You can't have a negative degree, can you?
No. Not here. Now, I think I'm going to prove this next time because I'd like to flesh it out a little bit more and not waste your time fumbling through it. But we can prove, what we will prove, one of the things we'll prove about the algebraic words. We'll go through the proof on page 187 to 188 probably next time and prove that if you have two algebraic integers, so here's a theorem we'll prove next time. Sorry, I will eventually choose a spot, Cameron. So the main theorem, this is a little bit above our pay grade this semester to prove that the algebraic numbers form a field. That would be harder. But this theorem we can prove, which is that if alpha and beta are algebraic integers, then alpha plus beta, alpha minus beta, and alpha times beta are algebraic integers. All right. And the proof of that is pretty slick. That's, I think, one of the things that Dedekind brought to bear in the late 19th century. He used determinant to prove this. It's not entirely simple to prove this. But once you prove it, what does this say about the algebraic integers? They form a what? A ring, exactly. Because it's closed under addition, subtraction, and multiplication. Is 0 an algebraic integer? Is 0 a rational number? It is, right? So its polynomial f of x is just x.
So, is subtraction a different operation than addition? Some people say, like, I heard, like, oh, it's just addition, you just add the...
Well, if you use subtraction to characterize things, that allows you to capture additive inverses. That's basically it. But yes, algebraists do have an irrational fear of subtraction for some reason. You're right. I mean, I don't know. There seems to be some animosity. Maybe it's the lack of associativity. I don't know. But this brings us to section 10.4, where there's something that is simple enough I can prove. I've been throwing this notation around. I wanted to try to settle it today. We'll get back to this technical thing that I just stated up there next time. But And I guess you could ask the more structural question. Well, maybe you don't need to, though, because everything's inside the complex numbers, right? So if you believe that the complex numbers exist, then everything I'm writing shouldn't be like the existential questions shouldn't be vexing to you. So, as he says at the start of section 10.4, he says the ring of all algebraic integers has some inconvenient properties, right? For example, there are no primes. What's a prime? P is a prime in a ring R what? If only P and it P excuse me, P, comma 1 and their associates, which I'll define shortly, guys. Associates are divisors of P. What's an associate? It's what? It's, let me be more specific. A and B, by the way, A and B are associates in R if and only if there exists a unit U such that what? B is equal to, yeah, A times U. So associates are simply, they're very closely tied to either P or 1. They're just a unit times P, or, so for example, if X is an element of the integers, it has associates what? Right, plus or minus. Well, yeah, it is. You're always associated to yourself. This cannot be avoided, right? So there's that. If you have X in the Gaussian integers, we have what? It has associates. Yeah, plus or minus X and plus or minus IX. In the Eisenstein integers, I'm not going to write it down. I'm tired of it. Enough. There are 6 associates in the Eisenstein integers for a given Eisenstein number. In one of those awful things over there, there are infinitely many associates. In the Hurwitz integers, 24 associates. And probably I need to talk about left and right, but whatever. Okay, so that's a prime. So one of the things he points out at the start of section 10.4 is one of the annoying things about algebraic integers is there are no primes. Why is there no prime in the algebraic integer? Well, the example he points out is just this. He's like, why primes are hard to find. In the algebraic integers. I don't have a symbol for that. It's starting to annoy me. What's that?
I'm sure you can make one up.
I can make one out. AI. Well, check it out. If alpha is an algebraic integer, right, you can always just go, so like square root of alpha times the square root of alpha. And so alpha is divided by the square root of alpha. You can prove that the square root of alpha is also an algebraic integer. So every algebraic integer factors into other algebraic integers. You're like, how many algebraic integers are there? There are a lot. There are a lot. I think they're countable, though. Fun fact. Rational numbers are countable. Same cardinality as the integers. That's weird. But anyway, let me stop making weird but useless comments. So there's no primes in the algebraic integers. That's kind of a drag. We like primes. Which brings us to the study of basically subsets of algebraic integers is really what we're looking at. So we don't look at all the algebraic integers. We look at some subset of the algebraic integers which are built over something in particular. The things that they're built over, most typically for us, are these so-called quadratic fields. Okay, so so here's the definition. I think this is a good definition. He hasn't quite said it. Well, he kind of said it. Let's let D be an element of Z and D not a square. Okay, or you could say D is square free if you like. Then Q, parentheses, square root of D, is the smallest field the smallest field containing Q and the square root of D. All right. So here's the theorem. I think we can prove this today. Now you say, what do you mean smallest field? I mean, no extra points that you don't need. Like, so in other words, smallest field means it's the smallest set which contains both the rational numbers and the square root of D. Square root of D is something which is in the complex numbers, right? It's either a real number, it's an irrational number, because D is square free, or it's I times an irrational number, because D could be negative, right? For example, D could be minus 1. Okay. That would be, okay, so to say it's a field just means what? It's closed under addition, multiplication, subtraction, division, right? And we also, I mean, we should, to be clear, we do need that the number 0 is in there and the number 1 is in there pretty much, right? So here's the theorem. It's simply this, Q, the extension field, Q adjoining square root of D, is equal to, well, it's equal to A plus B times the square root of D, such that A and B are rational numbers. Now, that is what we called before Q square bracket D. Again, the square bracket D, to be more careful, it just insists it's closed under addition, subtraction, and multiplication, but no division, right? So what do I have to do in order to make good on this claim? I have to show you that the sum of two of these is another one of these, right? Sum, difference, and multiplication. So let's do it. So proof. So, you know, A plus B squared root of D, comma, let's say X plus Y squared root of D, and this guy. I guess I should say, to be not logically assuming, I'll say the square bracket to start with, because that's something we defined already. So I'm not begging the question. But, I mean, this notation says that this is a field. So you add them or subtract them, right? And what happens? You just, I mean, the definition, I mean, these are complex numbers. I don't get to define a new addition or something, right? Addition's already defined for me. These are complex numbers. So it's A plus or minus X. Oh, excuse me. Yeah, A plus or minus X, parentheses, plus B plus or minus Y, close parentheses, other parentheses, square root of D. my very non-sophisticated observation for you is that this is an element of the rational numbers, and this is an element of the rational numbers, right? So therefore, this whole thing is an element of q square bracket square root of d. In other words, it is again of the form integer linear combination of 1 and square root of d. Excuse me, rational linear combination of 1 and root d. This is a rational linear combination. Multiplication. Again, not that hard to do. You just multiply, right? And what happens? You get you get ax plus the square root of d times square root of d gives you back a d, and you get plus dby parentheses plus parentheses ay plus bx. Man, we have done this algebra a lot this semester, yeah? Of course, the things in parentheses are what? Right. So therefore, this also is an element of Q. You know, that is again formed from rational linear combinations of 1 and D. By the way, I was debating whether or not you need to put 1 in the brackets. You don't. He defines it carefully in this chapter. He was just using that notation as a label before. He's defined the notation in this chapter. You know, some of the things I was worrying about earlier in this course have become clear in chapter 10. Here's where he actually tells us, carte blanche, you know, like, this is the definition. And then if you go back and look at things I was worrying about before, often they're solved in chapter 10. Then what's left to show the field? What do we need to do? Division, right? Now, it suffices to show that the reciprocal exists, right? Because if the reciprocal exists, then we'll just say, you know, we can always say let me say z over w, right? Z over w is really just equal to z times 1 over w, right? So essentially, I just need to be able to show that 1 over w exists. So what is 1 over w? Or let's say 1 over... Excuse me. Oh, I'm sorry, guys. A plus b squared of d. So what can you do? Assuming this is non-zero, remember, in the field, we don't have to show 0 as a multiplicative inverse. It's not part of being a field. It's not part of pretty much anything. So we suppose that we're looking at a non-zero element. Right? If that's not 0, that implies that a minus b root d also is not equal to 0, right? And that's a complex number. Right? I mean, in fact, more to the point, you can multiply this by the conjugate, right? What happens when you do that? Yeah, we got the norm downstairs, right? That thing again working its magic. So we got a squared, yeah, minus b d, yeah, minus, well, b squared d, I suppose, right? Yeah.
Just because the division of it is not equal to 0, how does that imply subtraction method?
Well, it's because d is, okay, that's a good question, Sharon, actually. So this requires something we proved earlier on. D is square free, so that means that this is irrational. So we proved earlier that if you have something like, you know, I mean, okay, so it's either irrational or it's I times irrational, okay? And we proved earlier that if you have such a linear combination, that the coefficient, the real coefficient, and then the part next to the square root, they have to be independent. And so they separately have to be 0. So like this being not 0 actually implies that, and we proved this earlier in the course actually, implies that b is not equal to 0 and that I can't. A is not equal to 0 and b is not equal to 0, which then tells you this. Or you could work with the conjugate. I mean, look, if I want to make this simpler to understand, what I'm really looking at, it's an algebraic, it's what's the name of this thing? Something in Q adjoining square root of D, it's a complex number, right? So I could just as well call this thing 1 over z, right? And the formula basically for figuring that out, you just multiply by z bar over z bar, where that's the conjugate. Certainly if z is non-zero, its conjugate's non-zero. And what you have here is just z bar over z bar. Now z bar is the norm of z, as we've discussed before. And so this is, this thing downstairs, despite the appearance that it might be 0, can't be 0. All right, because it's actually the norm of the complex number, despite the minus being there. So what I'm trying to say is this is non-zero, and that's there's nothing surprising about this calculation. This is how we always find the inverse of a complex number multiplicatively. We just multiply by the conjugate over the conjugate. Okay, so details, your familiarity or lack of comfort or discomfort with that aside, is this again of the form rational linear combination of the number 1 and the square root of d? Well, yeah, I mean that's a over a squared minus b squared d minus b over a squared minus b squared d times the square root of d. So again, it's an element of Q, square bracket, square root of d. Which means we don't really need to use square brackets because we just showed that this set is closed under addition. It's closed under division as well. Okay. In fact, I'm only really justified in using the square bracket notation if we have also shown that it's closed under addition, multiplication, and subtraction. Which is why you did that earlier in the homework problem. Remember that homework problem? Where you showed that the subtraction and multiplication of those Gaussian integers was again a Gaussian integer. That's why this notation, z square bracket I is reasonable. But, he didn't really come around and define that carefully until chapter 10. Excuse me. All right, let us collect our thoughts. So we're trying to understand this ring concept, this field concept. We're trying to understand divisibility, primes, what it means to define algebraic integers. We're on the road to that. Now, I will tell you the other major theorem. The other major theorem here is so we actually did prove that. That's good. The other major theorem here is the integers of Q square root of d. So in other words, so what he's really saying is, what is the intersection, all right, of that set of algebraic integers? What's the intersection of AI and this set? All right, what are the so-called integers over this so-called quadratic extension field? The quadratic extension field is said to be an imaginary quadratic extension field if d is minus, and it's a real quadratic extension field if d is positive. D is square free in either case, okay? well, I guess if it's something I'm saying is slightly wrong. Anyway, let me get to it here. When D is not congruent to 1 mod 4, the integers, and I do believe he means algebraic integers, okay, of Q, the field adjoined by, the field, smallest field with square root of D in it, are of the form A plus B square root of D with A and B integers. Right? That's like point number 1. Point number 2, he doesn't have these numbers. But these are the two cases. When D is congruent to 1 mod 4, all right, the integers of Q adjoin square root of D field, quadratic extension field, are of the form A plus B root D with, now here's the kicker, with A comma B in Z, or A plus a half, B plus a half in Z. The proof of this is on page 190 to 191. I understand parts of it right now. There's a few steps I'm a little bit fuzzy on, so that's why I didn't want to do that today, until I get rid of that fuzziness. The theorem I quoted earlier I do understand, but I don't have the proof written cleanly yet. This is slick, this way of saying it. I have said before just that A and B are in a half C as a substitute for both of these together. But this is nicer because it really separates the two things. You either have integers or so-called half integers, right? So like half, plus or minus a half, plus or minus 3 halves, plus or minus 5 halves, and so forth. This is a way of saying that cleanly. Duh. So can you guys think of examples of this already? I mean, I'll prove it next time, but what are our examples? How about, let's see here, how about Q of the square root of minus 1? So notice that minus 1 is not congruent to 1 mod 4, right? And what were the integers? We actually had the Gaussian integers were the integers of this field. On the other hand, the thing that was funny basically was when we looked at this one. Right? Now minus 3 is congruent to 1 mod 4. Right? And that's why we looked at Z with zeta 3. Those are the Eisenstein integers, which involve those half integer combinations. But that's it. That's all that's out there for these quadratic fields. It's either what we've seen or it's the halves. Those are the quote-unquote integers. However, as I mentioned earlier today, many of these quote-unquote integers fail to have the unique factorization property. So if you insisted on that as being part of what integers are, you'd say this is bad terminology. And that's what chapter 11 starts to be about, is these ideals, this notion of an ideal which fixes the failure of unique factorization. But more on that later. That's all I got for today, guys. Have a good weekend. I think if things go well, if I have my act together, I think we're going to have, even a little bit of time to talk about the test before the test happens. So we'll see.